All right, so we're gonna continue on chapter 28, and I put a few other things in the lecture that might not be directly out of the book, but related to the book. So I thought we'd start off talking a little bit about what a clean room is. Okay, so here's a photograph of a clean room. This is a very modern one. On the ceilings, you can see what they call the wafer transport port tracks. So it's all robotic. So the wafers are in pods that travel along the track on the ceiling. And then when it gets to a specific tool, the front opening universal pod will be lowered down. Oops. Be lowered down from the ceiling onto the tool. So you can see some of the input areas around here for loading up the different tools. And it's highly automated. So this would be like a Global Foundries fab or an IM Flash or one of the more modern Intel facilities. So you don't see very many people in there. Most of the loading, unloading, and that sort of thing is done by computers and robots. And the engineers, technicians work in pods. They call them pods, computer pods, or rocks, remote computer systems. So see, I got somebody in the chat. All right, so anyway, so a lot of the work done in these ultra modern fabs is done outside of the clean room, and occasionally somebody will have to go in and fix something or retrieve something out of a stalled tool, or repair something. Okay, so the modern clean rooms kind of look like this. Most of the MEMS clean rooms and biotech clean rooms and that sort of thing are more manually driven, because they do small number of products, relatively speaking. So it's not cost effective to have all of these robotic systems and highly automated systems. They'll never make their return on investment. All right. So let's think about this. If you're managing a clean room, all right, and you want to know how clean it is, can any of you think of any kind of a metric to be able to judge how clean a clean room is? If you have an idea, go ahead and type it in the chat box. A few people have responded. Particles per cubic foot, parts per million of dust in the air, ppm of particles in the air, ppm of particulates, parts per million. That's an interesting number to come up with, parts per million. Think about that. Parts per million of what? Usually we use parts per million when we're talking about the number of molecules relative to the total number of molecules. So it's for like toxic things, for gases, that sort of stuff. So particles per million molecules of air isn't really the best way to measure how clean the air is if you're talking about air quality, right, in a clean room. So the number of particles per cubic foot is on the right track. Okay, and we have different ways of doing that. So here's a graphic. Here's a graphic of particles per, let me arrange my screen here a little bit. So we've got particle diameter in the x-axis and total number of particles per cubic foot on the y-axis, okay? And they're also saying it's got to be equal to or larger than the stated particle size. Okay, so for example, if you're a class 1, that would be 1 particle per cubic foot, okay, which is a volume, particles per volume. But then what size is that? you know, greater than a half a micron, greater than 1 micron, that sort of thing. So that depends on what you're making in your clean room. If you're making relatively large things where the minimum geometry might be a micron or 2 microns, then you might say, okay, I want to classify my clean room relative to number of particles greater than a half a micron. Because I know if it's a half a micron or bigger, there's a chance it could short out or cause a problem in my small devices. Okay, so I would classify it as a class 1 or a class 10 at 0.5 microns. Now, if you're Intel and you're making extremely small devices that are highly packed, then you might put in, oh, I have a class 1 clean room, which would be 1 particle per cubic foot, but then that's for particles greater than maybe 0.3 microns or 0.2 microns. Okay, so when you talk about a clean room class, a classification of a clean room in terms of its cleanliness, you're talking about the number of particles per cubic foot at a given size or bigger. Okay, so that's kind of what you're going to look for. All right, so you can see this classification, right, would show you've got the particle diameter that you're thinking about qualifying your clean room, say half a micron. If you go straight up, it's a class 1. At this point, it would be a class 10. At this point, 10 particles at half a micron or bigger, right? But it changes as a function of particle size. Okay, so that being the case, you can see the different classifications, but also notice that there's an ISO classification next to it. So the international system of standards, the ISO classifications, are so many particles per cubic meter, of course, at a given size. So they have a slightly different way of defining it, but it directly relates to the classification scheme that the US started when we started doing clean rooms back in the, oh, I don't know, we probably were doing clean rooms back in the early 60s or so. Just a trivia note, clean rooms were invented at Sandia National Labs. And HEPA filters, which are used to keep the clean rooms clean, were invented at Los Alamos National Labs right around the time of the Manhattan Project and shortly after that. So New Mexico is the inventor of clean rooms. All right, so let's think about this. We're engineers, right? We want to know, how do you keep it that clean, right? How do you keep it that clean? Well, this is a schematic of what a clean room system would look like, and this is similar to the one we have at the MTTC, which is the UNM clean room, one of the 2 clean rooms we have on campus. And you have an outdoor unit that pulls in air from the outside, okay? We filter it there, right? So we get 99% of the particulates out of the air, outside in the outdoor filters. So we have different types of filters, electrostatic filters, and then some coarse filters and some finer filters. And then we push the air through into the clean room through these other HEPA units here, these little boxes on top, and that pushes, and we push very clean air into the clean room. So the HEPA filters get rid of most of the rest of the particles, and depending how good of a HEPA filter you have determines how clean the air is and what class of clean room you can get to. So our MTTC clean room is a class 1000 at half a micron, but if you don't have people in it, it probably is better than a class 100, which is fine for what we do in our clean room, right? For research and small volume production and relatively large large devices, right? Bigger. We make things. The smallest part is bigger than a micron typically in our clean room. Okay. So that's the overall design. And then if you look at one part of the design, you've got the central air handling unit here that's pulling air from the outside and then pushing it down through the HEPA filters. Okay. So there are fan units here that push the air or pull it through the HEPA filters into the clean room. And then you get more or less laminar airflow. It goes straight down. Okay, and then it comes out on the left and right sides at the return. So in our clean room, we have them just above the floor on the sides of the bays. So the air comes down and then goes out through the sides. Other clean rooms, they actually have an open floor and the air gets pushed through the floor into the subfab and then it's recirculated there. So you get a return duct. Okay. And some of the air gets pulled out through the ventilation systems and through the fume hoods because you have fume hoods in there for doing chemistry. So then you have to make up the air, right? We don't use the same air over and over again. There's a makeup air unit. So we get fresh air coming in as well. Okay. And then here's a close-up of what the air filter looks like. So you have a folded design. So you can see this yellow part here is folded. And that's basically your filter, right? And it wraps around these stainless steel structures to keep it stiff. Okay, so you have a lot of surface area here, right? You need a lot of surface area because the pores, if you look at the fibers in the HEPA filter, the holes between the fibers is pretty dense. So trying to push a lot of air through very small holes is difficult to do. It's kind of like drinking cappuccino through a Starbucks stirring straw that's very thin. It's really hard to do that to get a lot of flow. So one way to improve that is to have lots of those straws, right? And then you have a little bit of flow, but lots of holes. So the more holes you have, even though they're small, the more flow overall you can do. And that's why the HEPA filters are usually pretty tall. And then the filter is wrapped around like an accordion design. So if you've ever replaced your cabin air filter in your car, you can see it has kind of like a zigzag structure to it, and that way it increases the overall surface area that the air can get pushed through, so it's easier to push the air through. Okay. So how do you measure particles per cubic foot? Anybody have an idea? There's a little unit on the left. Anybody have an idea how those things work? Right? These units will tell you a distribution. Okay. Geiger counter. A Geiger counter is if it's radioactive. Right? It looks like a Geiger counter though. So, you know, if you're an engineer and you were going to count how many particles per cubic foot are in the air, how would you do it? How would you create a device to do that? Brendan says use light. Yeah, that's a good idea. If you ever look, like when you have bright light coming in through the window, you can kind of see the dust in the air. The reason you see the dust is the light is scattering off of the dust. Okay, so you get a haze. All right, Eric says they pull a specific rate, probably a specific volume per unit time, and measure based on how many particles you encounter over that time. That's correct. But it's tough to measure the particles, right? The number of particles and the size. Look, you get a size distribution as well. The basic idea is if you run a laser beam through an air sample, particles will scatter light off of it, okay? And then if you look at a right angle, like basically to a right angle or at some angle to that laser beam coming in, If you see a flash of light, that means, oh, it reflected off of a particle. And if that flash of light is more intense, it's probably a bigger particle, right? So they calibrate these things based on the intensity of the scattered light from one particle. So the intensity is correlated to the size of the particle, approximately. These aren't perfect, but they do a lot of traceability standards and testing. And then they get a count for each particle. And they can get pretty high. So I think this one can do like 2 million counts per cubic foot, and then it gets saturated, right? And there's too many reflections for it to count them all. So, so the table on the right gives you an idea of the distribution. Okay, so we've got 699 particles at 0.3 and 349 at 0.5, et cetera, et cetera. So think about this. What class of clean room does this data represent if you're using a 0.3 micron threshold? So that's counts per cubic foot. So can someone put something in the chat box to estimate the class of clean room that this data would represent? Class 1000, class 10,000, class 100, class 10. Well, let's take a look at it. We've got a 0.3 micron. We're getting about 700 counts, and we got 350 at 0.5. Remember, it's 0.3 microns and bigger. So if you were to add all of these up, that would give you an idea how many counts or how many particles per cubic foot, right? That's larger than 0.3 microns. Okay, so by looking at that, you got 700, 1,050, 12, 13, 14, about 1,500. 1,500 or so particles per cubic foot. So if you said you were a class 1,000, you would be kind of cheating it a little bit. So you'd say you're a class 10,000 or better, right? So as an engineer, you'd say, well, let's try to reduce the number of particles per cubic foot, and then we can say we're a class 1,000 or better. Okay? All right. So this is a sample question, right? What class is this? So, you look at about 0.3. Well, let's say we're going to classify it with 0.5 micron or better. Maybe our clean room, we don't make really small things. So then you just take a look at the counts that are above 0.5 or 0.5 or more. And if you add these up, you got what, 5, 6, 700, something like that. So you get, and then you look at 0.5 and you just go up until you get to 700 here, and it crosses with the 0.5. So we're an ISO class 5 maybe. Let's see, what are these? Yeah, I think the ones in the parentheses are per cubic foot, and the one that's not in parentheses is per cubic meter. So we're talking about cubic feet greater than 0.5. So we come up and we're up here somewhere, class 100 to class 1,000 in that range. Okay. All right. So, we saw a video on making things in a clean room, and there's several posted online. So, and they talk a lot about making semiconductors. That's probably the #1 thing made in clean rooms, right? We make computer chips, lots and lots of chips. You open up your cell phone, your computer, your laptop, your toaster, you name it, it's probably got a computer chip in it, okay? And the basic part of a computer chip is a transistor. And most transistors are based on MOSFET, which is metal oxide semiconductor field effect transistor. Okay, so that's probably the most type of transistors made. Okay, so MOSFET stands for metal oxide semiconductor field effect transistor. It's a mouthful, right? And we use the CMOS process to make them. So that's complementary metal semiconductor. Let's see, CMOS would be complementary semiconductor metal oxide semiconductor. No, yeah, anyway. Let's just go through the method of making it. So this is how you fabricate it. So you start with a crystalline silicon wafer, which we talked about a little bit already, right? It's pure crystalline. It's been doped, making it P-type, okay? And then we put a very thin layer of silicon dioxide on there, and that's done by growing it. You grow the silicon oxide. So you basically put the pure silicon wafers in a furnace, and then you heat it up to 1100 degrees Celsius or so, and you cause the silicon to rust and put a little oxygen in there with it, okay? So you can rust the crystalline silicon. That's called oxidation. So you create SiO2, silicon dioxide, and you create a thin layer of oxide. So that's an insulator. And then they usually deposit silicon nitride on top using chemical vapor deposition. Silicon nitride's typically done also at high temperatures and in an environment that contains ammonia and silane, so, or dichlorosilane, one or the other. So you have a silicon source, and then you have a silicon source, and then you have a source of nitrogen in the ammonia. And you can grow silicon nitride. Okay, so the first step is to create this on your wafer. Now we're looking at it from the side view. So we're going to build up our transistor and look at it from the side view. Okay, a cross-sectional view, like you did in D1 when you did cross-sectional views of larger widgets and things like that. Okay, and then once you do that, you pattern it, right? So you make you leave some of the silicon nitride and oxide behind, but you remove the silicon oxide and silicon nitride from certain areas. And then we do a boron implant. Okay, so we're changing the electrical properties of the crystalline silicon in these areas. Okay, and the way you do an implant is you strip an electron off the boron that makes it positively charged. Then you can accelerate it in an electric field, make those atoms go really, really fast, and then they crash into the crystal. They also crash into this area here, but this stops it from going into the crystal, and here we allow it to go into the crystal. So we do our boron implant. After that, we grow, right? The light blue region is the boron implant. The green region is now a silicon dioxide. So we grow silicon dioxide again, okay? And then we put polycrystalline silicon down, okay? So in between the previous step and this step, we've stripped off the silicon nitride and then the silicon oxide we put down at first. Okay, now the polysilicon, okay, is going to be a conductor. Okay, so now we've deposited the polysilicon. Okay, and then we remove it from everywhere except right here in this little bump in the middle. We do a phosphorus or arsenic implant, and that changes this part of the crystal to a different type of doping. So you got N-type, P-type of regions, okay? And this little piece here, this little blue bump or purple bump, that's going to end up being the gate, okay? It's also protecting the crystal from getting implanted in that little region here. That's going to be your channel, okay? All right. So once you do that, right, you do some more patterning and etching and deposition. So we put a little bit more silicon dioxide down through chemical vapor deposition. This was grown. This is deposited. Okay. And now you have these regions. You put metal down. That's your source. It's made out of aluminum. Okay. So you have your source and gate, or your source and drain. That's the metal. And then the polysilicon comprises the gate. Okay, so now you've got your three connectors for your transistor. Remember, we're looking at it from the side view. Those connections come out of the page, right? So now you've got a source and a drain and a gate. Okay, so remember that video we saw before about the transistor just being a switch? Well, when you put a voltage on the gate, it causes conduction to happen between these two, between the source and the drain. Okay, so if we put a voltage on the gate, it allows you to connect, right? And you can do this very quickly with varying voltages. Okay, so you can turn that transistor on and off very, very quickly. And that's basically how you make a MOSFET. Okay, very simple process, costs a lot of money, is a lot of equipment, and the smaller you make it, the more expensive it is and the more precise you have to be. It goes back to what we learned in design 1 with tolerancing. The tighter the tolerances, the more expensive it is to make. All right, so let's jump back to crystals. Okay, can somebody volunteer in the chat box what crystal structure silicon is made out of? It's either FCC, BCC, diamond, or hexagonal. Silicon's pretty much a diamond structure. Okay. So this is one way to refer to it. Okay. I think we did this little thing in class previously when we talked about crystals, right? About the different crystal structures. So you can go to this link here and look at different crystals and look at them from different views. Okay. The reason crystal structure is important is you can make things with different shapes depending on the crystal structure. Okay, we're going to skip that. Let's look at this one a little bit more closely. So this is a basic unit cell. It's not that of silicon, but it's just showing you where the corners of the cube is. And I'm going to give you a little bit of a handle on Miller indices. I believe we did this in a previous chapter, but it's worth reviewing. So the way you show what directions there are in a crystal is you look at it in terms of a Cartesian coordinate system. So if I take one step from the origin in the direction of X, and no steps in Y, and no steps in Z, okay, I've just gone in the 1, 0, 0 direction. So that defines a direction. It's kind of like saying north, right? If I take one step in X and one step in Y, and then I connect those two dots with a vector, then I've gone into the 1, 1, 0 direction, and etc. Now the planes you see, okay, we're showing 3 planes of the cube. Those are the planes perpendicular to those directions. Okay, and there's a lot of online stuff about Miller indices and how to do the directions and that sort of thing. So you can go ahead and do some research until you can actually see it. But the whole point is that you can define the planes based on the directions. They're the perpendicular planes to the direction, okay? You can define other planes. So here's an example of a 1, 1, 1 plane. Is it A or B? 1, 1, 1. Remember, it's the plane perpendicular to the direction. Most people are saying B. You're right. All right, you go one step in X, 1 in Y, 1 in Z. Then you have a vector that goes from the origin to the opposite corner of your cube in this case. And then if you draw the plane that's perpendicular to it, you get that triangular looking plane there. That's how it lays inside the cube. Of course, the plane's infinite. It keeps going outside the edges of the cube, but you get the idea, right? Anybody want to venture to guess what plane is depicted on the left side in A? 110. All right. Okay, so the planes are defined by the directions, right? The planes are perpendicular to those directions. Okay. And it makes a difference, right? So what we've done to help explain this to students is we have, and I would do this activity if we had a live class, you know, we have two different wafers. One of them, I'll tell you, is a 100 wafer, and the other is a 111 wafer. Okay. So the 100 wafer will break in one type of orientation, and the 111 plane wafers will be breaking differently. Okay. So it just depends on the orientation of the ingot. When you do the seed crystal into the melt and then pull it out, the orientation of the seed crystal defines what orientation that final crystal is at. Now, the crystal structure itself is the same. It's just the orientation is different relative to how you slice the wafers. So when I say I have a 100 wafer, that means the plane that's on the surface of the wafer is 100. Okay, and when I say I have a 111 wafer, that means the surface of the plane, the polished surface of the wafer, is the 111 plane. Okay, so if you look at these two depictions here, right, you can see this is looking down one direction in the crystal, and this is looking down a different direction in the crystal. So I'll tell you the one on top is looking down the 100 direction. And remember, since it's symmetric, since the crystal's symmetric, it doesn't matter if it's 100, 010, or 001. It'll look the same, just like it does on top. So you'll look down that direction, and then the plane you see on the surface, when you look down in that direction, that plane is defined by the perpendicular vector in that direction. So I'm looking on this top view here, I'm looking in the 100 direction, or the 010 or the 001. Okay, so let's look at the top. If I were to hit this with a hammer, right, or a nail and a hammer, tap the wafer, since it's crystal, it's going to break. It's going to cleave along the crystal planes. How do you think it's going to break? Like it looks on the left or on the right? Anyone venture to guess? Left. Yeah, if I hit this top one, I hope you can see my cursor, right? It's going to break in 45 or 90 degree angles to that. And that's what you're seeing here. Okay, this bottom one, now if you look at this bottom depiction of the crystal, right? Now I'm looking down the 111 direction. Okay, so I'm looking down the 111 direction, right? Looking down it. And then the plane I see on the surface is going to look like this on the nanoscale. You're going to see the atoms arranged in this way. And you can almost imagine that it'll look triangular when I break it. And that's what you see on the right. So they're about 60 degree angles or so. That makes sense, right? They look equilateral. They look like they're equal angles, right? So that some of the angles, the interior angles of a triangle have to equal 180. So they kind of look like 60 degree angles, okay? And that's what you kind of expect. Now there's some nice links in the slides. So when you review the slides later on, click on the links, and there's a longer description with more animation and that sort of thing that you can look at, and it'll help you visualize this better. I know this is kind of hard to do in the lecture. All right. So why do we care about the crystal orientation? Different orientations will have different electrical properties and mechanical properties. You already saw the manifestation of the mechanical properties by how they break, how they cleave, right? But we're making computer chips on there. So it's mostly about how do the electrons flow in the crystal along that plane. So they'll flow differently. They'll have different conductivities and resistivities and whatnot, depending on the the direction you're trying to get that current to flow. So remember, we make the transistor on the surface, and we define that channel. It's important to understand how that crystal orientation is underneath that channel, because if you do it wrong, if you put your transistors in the wrong orientation, you'll get a different response of the transistor. So different voltage threshold when it turns on, the different amount of current that will flow at a given voltage between the source and the drain, and that sort of thing. We had a case at Philips Semiconductors where we put some power CMOS devices on a 100 wafer set of wafers instead of 111 wafers, and the whole product failed. It didn't behave electrically like it was supposed to. And it took us a while to figure that out, because we looked at how it was made, what the structures looked like. Everything looked normal, except someone figured out, oh, we used the wrong wafers when we started. Someone's asking, can you use it to create 3D pathways? You can use the crystal structure to make different kinds of mechanical structures like springs and proof masses and channels. And I think we'll show some of that. So great question. Brings us up to this point. This is a wafer that has silicon nitride on it. And then we etched some holes in the silicon nitride, and then subsequently etched the crystalline silicon. So you can etch crystalline silicon with potassium hydroxide, KOH. Sodium hydroxide works as well. That's drain cleaner. You can buy it at Best Buy. So if you put the silicon wafer in a solution of potassium hydroxide, it'll dissolve over time. Okay, but it tends to dissolve the 100 plane, right? It etches that much faster than the 111 plane. So you can see the sides of this hole that we etched, right, are very smooth and haven't etched away. And that's the 111 plane. And then on the bottom, okay, you have the 100 plane, which etches really fast. And it kept etching until it reached the silicon nitride membrane on the other side. Okay, and I think we talked about this in a previous chapter. You might have had some homework on it, or maybe it's this chapter you have that homework. Okay, so this shows you some scanning electron microscope photographs of different structures made and leveraging the crystal planes and that they etch at different rates. So you can see you can make different kinds of beams and cantilevers and whatnot by leveraging that, by leveraging the crystal orientation and how it etches in a wet etch. What's nice about using wet etch, it's cheap. You just need a bucket of solution. If you want it to go a little faster, you need some heaters in it. So you can do, 25 wafers at a time in a bucket, and it's cost effective, but you have to be smart on how you design it and understand how it's going to etch so you get the final structures that you're interested in. So the one on the left, okay, you can look at this and say, well, it could be a nozzle too, right? If you make this hole the right size, okay, the bigger the hole, the deeper it's going to go. If you make the hole smaller, right? Imagine if the hole was half this size, the 111 planes would meet and it would stop etching pretty much, right? So then you'd have an upside down pyramid. If you design it right and know the thickness of your wafer, you can etch down so you get a hole, but that hole is defined by how big the opening is on the opposite side when you're etching. So they actually use this method to make nozzles, right? Very fine nozzles, because you can go down to 1 micron nozzles, 2 micron nozzles. And when you do that, you can atomize fuel, for example, and then you get a very efficient burn rate because the fuel is extraordinarily small droplets. So you have a huge surface to volume ratio and they ignite right away, right? And you get a lot of bang for the buck on your fuel efficiency. You burn everything. You don't have anything left over going out of your tailpipe. So the trick in fuel injection systems is getting those nozzles just right. And this is one way you can make a nozzle. There are other ways to do that. Yeah, you could use it for filters too, right? If you get creative. Problem is they clog up really fast. So you have to be, you have to be kind of creative when you do it. If you have a huge array of tiny holes, then yeah, some of them will clog up. You may want to do some pre-filtering before it, that sort of thing. So you can be very precise as to what size particles you're going to let through. And that might be important if you're sorting virus sizes or cell sizes, if you're having a bio application, right? And also, if you look at this, you can make channels, right? You can make a V-groove in your silicon wafer, and then you have a nice channel, right? For fluid, microfluidics, and that sort of thing. SOCs, I'm not sure what abbreviation SOC, silicon on carbon? I'm not sure what you mean by SOC. System on a chip. Yeah, exactly. We have ChemLab on a chip, right? That's a system on a chip where you can do some chemistry on a very small device. The new antibody test coming out by Cepheid. Cepheid is a MEMS company in California. I think, is it Peterson? One of the founders of all the MEMS stuff back in the day invented Cepheid. Kurt Peterson, I think. Could be another fellow. But he started a company to do this sort of testing. And so once you know the chemistry, right, and you know what reagents you need, you can create these little microfluidic chemistry labs on a chip. And that way you can do point of care testing. So you can take a saliva sample, a urine sample, a blood sample, depends what you're looking for. It's kind of like the insulin tests, right, that they do for diabetics, tell you how much sugar you have. So you can test things very cheaply, right? Because making these devices, you can put thousands of them on an 8-inch wafer, right? And dice them up and throw them in a circuit board or a microfluidic test bed or whatever you're making, and it can get extremely cheap to do these kind of testings. So I remember I went to a dollar store and they had pregnancy test kits for $1, right? And so you think, oh, it's going to cost a lot less to make it. It's probably 10 cents to make one, right? So you could, theoretically, you could make COVID-19 antibody tests at less than $1 a piece. And that's what he's working on, right? He's got some out there. They're working. They're testing them. FDA's trying to approve them. So, from the engineering perspective, how do you do the plastic injection molding for the packaging? How do you make the microfluidic channels? How do you, turn it on? Like, how does it know when there's blood in there? So there's all kinds of techniques used. I think the Cepheid one actually does a DNA test. So the sample goes in there and it goes through they call it PCR, where they cycle the sample and multiply the DNA, or maybe it's RNA they're looking for, one of those two. And then when they get it, when they cycle it enough, they'll have a strong enough DNA signal that they can detect it, if that DNA sequence is in the sample. So they look for a specific sequence, and then that tells them whether or not you have the antibody. Okay. Let's see, what do we got here? Yeah, so those tests work only 30% of the time. Yeah, I mean, quality control is an important thing. It depends who's making your devices and that sort of thing. So some of the cheapo ones in the dollar store, you know, you probably want to buy 5 of them and then take a vote. 3 out of 5 positives means you're pregnant. I don't know. So, but the point is that you can make detection systems pretty cheap, right? And you could do it at home. So that's what we're driving towards, those DNA testing things. If you're looking for a specific marker, you can make it on a very small gadget if you're just looking for one thing. Okay? And microfabrication enables you to do that. So that's what chapter 28 is about. How do you make really small things? And you need small electrical circuits, you need small microfluidics channels and that sort of thing. Because one, you don't want to use a lot of reagents to look at a sample, because that costs money. So if you can keep the chemicals down to a bare minimum, and you don't want to take, you know, a vial of blood, you know, you want a pinprick, right? So the smaller amounts that you need, and the smaller the units and all of that you need, the cheaper it is overall. And the less you have to transport. So you can transport 10,000 tests instead of 100 tests, right? If the tests are this big, you can't fit as many in a box than if they're this big. Okay? All right. So here's some more pictures of what you can make in crystalline silicon, taking advantage of the crystal structure. So here the 111 planes actually etch down in the potassium hydroxide till they hit a point, and then they basically stop. So you can have a very well-defined depth, right, by defining the opening. Okay, you can also go the other way. So Tyndall National Institute is where Dr. Jackson worked for, I don't know, about 11 years in Ireland, and they were making needle arrays. So you can actually make very fine needles, right? So these are extraordinarily pointy. They're taking advantage of the crystalline lattice structure to make these very pointy things. And having very small needles makes it so you don't feel anything. So if you make 10,000, 100,000 of these needles in a couple square centimeters or so, you can make a patch. You coat the needles with whatever drug that you want to administer subdermally, and you put the patch on, and it only goes in so far, which you define as an engineer on how you etch these things, you know, how big it is. You won't feel the patch going into your skin because it only goes about 3 or 4 layers in, and it stops before it hits the nerves, but it's past the top few layers of skin cells so the drug can get delivered. So this is a painless or less painful method of doing drug delivery. And then you can coat it with timed release drugs and that kind of thing. And you have a wider range of therapeutic options as a doctor, right? That sort of thing. And then you can make little pyramids with flat tops too, if you need to make something that looks like that. Okay. All right. So how do you make these things? Okay, they're using, I'm looking at the chat box, they're using that for the COVID-19 vaccine trial from Penn State. Awesome, I did not know that, and I'll have to look that up. I got a buddy at Penn State who works with micro nano education out there. All right, so how do we do this? Well, we gotta design something in CAD, right? So, and remember, it's a layer by layer by layer by layer. We build up layers. So each layer is a different design, and all the designs or all the patterns will align to each other. So the layers will make sense, and you end up with a chip or with a MEMS device. So you design the layer in CAD, you design all your layers in CAD, and then for each layer, you manufacture what's called a photomask, and that's what we're showing on the left here. Okay, so that's just the pattern for one layer. Okay, so you can see it has light regions and dark regions. So light can go through the light regions and light cannot go through the dark regions. So it's called photolithography, or lithography for short. So the lithography is a step in the manufacturing process that transfers the pattern to the wafer using light-sensitive materials, okay? So here's a picture of what it looks like in CAD on the left. This is a simple, actuated cantilever beam or something like that, okay? And then on the bottom right is a test mask with a bunch of different structures on it that engineers use to set up their processes and understand where the tolerances are, okay? And I think the thing on the bottom left is a mask making tool. So you coat a piece of glass, usually it's quartz, with chrome, then you put a photosensitive material on it, and you do an electron beam drawing of the pattern that comes directly from the CAD file, and you draw it on the photosensitive material, and then you develop the photosensitive material where the electron beam is hit, and whatever remains will protect the chrome underneath, and then you do an etch of the chrome. So the exposed chrome goes away, the chrome that's protected stays on there, and you get the pattern you see on the bottom right. Okay. So the light goes through the photomask. That's the main concept you have to think about, right? So, if you have light going through something that has black and clear regions, what are some of the important properties of light that affect the quality of the image you're going to project, or you're going to project through that mask? Any ideas? Wavelength. Cool. Or wavelength. Yeah, so wavelength is real important. You can imagine if you have a long wavelength of light compared to a short wavelength of light, right? The longer wavelength, you can't image things that are as small as you can with smaller wavelengths of light. And then smaller wavelengths of light, right, have more energy per photon. So you need a certain amount of energy in the photon to get the chemistry going, right? You want to do something to that photosensitive material. So if you have an infrared photon, it's not going to have enough oomph to do anything in the chemistry to get the chemical reaction going. So you generally want green or blue light or something, deep UV, X-ray, that kind of thing, to give you more energy per photon so you can do more with it. And also, you have a smaller wavelength of light, which allows you to pattern smaller things. Okay? So that kind of makes sense. So here's a cartoon from the book. It's a table showing the different wavelengths and how small you can print. So finest feature size in nanometers is how small you can go with a certain wavelength of light. Okay, so if you're using ultraviolet light, standard photolithography, this is 365 nanometers, which incidentally is the eye line of the mercury arc spectrum. So we use mercury arc lamps for most photolithography, and there's a very strong line at 365 nanometers. So we isolate that line with filters, and we use that to image the different patterns onto the wafer. And by playing some tricks with the photomask and doing things creatively, we can get down to as small as 350 nanometers structures. Now, typically in production, when I was working in the industry, when we used eyeline, you know, half micron was fairly easy to do. Much less than that, we had to play some tricks. So you do things with the mask to take advantage of interference effects and phase shifting and that sort of thing. So that's a real high level of optics that you got to work with. Okay, so deep UV would be the next next range, and that's a certain, I think that's a certain laser, argon krypton laser light source. If my memory serves, it might be something else. Extreme UV, now we're down to 10 to 20 nanometers. Then we have X-ray. So they do some X-ray lithography, but it's extraordinarily expensive to do that. Electron beam lithography, that's really precise. You can actually get smaller than 80 nanometers now with electron beams, but it's slow because you're drawing, you know, you're drawing the pattern out. You can't just do it all at once. Okay, like with a photomask, we shine light through the entire photomask and we get the whole pattern at one time. The electron beam, you know, it's got to draw it out. So making a photomask with an electron beam takes a few hours. You can't go into production making a computer chip and it takes you an hour for each one just to draw one pattern, and then you have to do 50 patterns to get the full chip. You know, that's not cost effective. Now, if you're doing research, you know, and you're just wanting to make one little structure and test how it works, yeah, electron beam lithography is actually really good. It's kind of like a 3D printer, right? When you make one prototype on a 3D printer, that's great. You know, you can wait a few hours. But if you're going to make 10,000 parts on a 3D printer, you either need a lot of 3D printers or you need to speed them up somehow, okay? And then there's immersion lithography, which is kind of fun. They use 193 nanometer wavelength, but they actually print in water. So they'll have a film of water on top of the wafer. So they don't have the issues with the air. Okay. So here's a mercury arc lamp spectrum. I already mentioned the I line, which is 365. When I started in the industry, we were using G line, 436. And then within a year or two of me starting, we jumped to I-line. Okay, I-line's a little trickier. With G-line, you can use quartz optics, right? Regular glass quartz. But with I-line, you had to use calcium fluoride optics, and that's why there was a delay from going from G to I-line, because you needed different kinds of optics, and which were tougher to make. The price of a G-line stepper, you know, maybe $500,000 or something like that. The price of an I-line stepper was $4 million. And the lens by itself was $2.5 million. Okay. So, you know, when you go to smaller geometries, you have to have better equipment, better materials for projecting and all of that. Okay. So, you know, like I say, the mercury arc lamp, that's HG, stands for mercury, in case you didn't snap to that. Mercury lamp typically used, we could go down to 0.8 microns or so with G-line if we worked on it. And I-line, we could do half a micron, maybe a little bit better than that if we were careful, okay? All right, so what affects the minimum geometry you can print with lithography, right? So that has to do with light. Okay, so if you look at the minimum resolution equation on the left, right, you got lambda, which is the wavelength, okay, in the numerator. So the smaller lambda is, the smaller the resolution. And resolution is how well you can image something like two dots next to each other, right? If I have a longer wavelength, the two dots are going to look like one dot. They're going to merge together. And if I use a lower wavelength, I'll be able to resolve them separately. It's kind of like looking in space at binary stars, right? When is that spot in the sky? When can you tell it's two stars next to each other rather than just one star? Well, you have to have a good resolution telescope. Same is true when you're printing stuff. The higher the resolution, the finer the structures you can print. The finer the structures that you print is dependent on the wavelength of light you're using. So lambda is the wavelength of light, okay? And NA is the numerical aperture. So that's determined by how you make your lenses. So the lens designers try to get the numerical aperture as big as possible to get the smallest resolution. So if I can raise the numerical aperture for a given wavelength of light, right, I can print things that are smaller. So the competition between the companies that make these exposure tools that project these images, they're typically Canon, Nikon, ASML are the three big ones, right? Their lens designers are always trying to push the NA to be as big as possible. So when you increase the numerical aperture, you can make things smaller. And K has to do with what photoresists you're doing and how you're projecting it and all of that stuff. Okay, and you find that experimentally for the given piece of equipment you have. Okay, so that's resolution. So you'd say, oh, okay, let's go to the smallest wavelength we can and the biggest numerical aperture and we'll be good. The problem is when you do that, your depth of focus also changes. And the depth of focus is how well you can focus over what range. Right? So if you have a big depth of focus, then you can easily pattern things, even if the topography of the wafer is a little bit higher, right? A little bumpier. Patterns or the surface you're trying to project the pattern onto, which happens because as you saw when you're building these chips, you get hills and valleys, right? So you want everything in focus when you print some higher level pattern onto the wafer. So if you look at the right equation, you've got lambda over NA squared. So if I increase my numerical aperture so I can get smaller resolution, my depth of focus goes out the window, right? So then now I have to solve the focus problem, right? I got to either make everything flat that I'm projecting onto so I can polish maybe in between layers to flatten things out. So I put a layer of oxide and then I polish it and make it flat. So maybe I can get rid of the variation in topography that way. Okay. So that'll help, right? But also when I go to smaller wavelengths, my depth of focus goes out of whack. I can't focus over as big of a region in space. Okay, so you've got competing things, and that always is what happens in engineering. You get a better or stronger material and it costs more, or it's harder to make, or if you don't make it right, it becomes brittle, or you're always balancing these things when you're designing. Okay, so here's an example, right? This is what I'd have you do in class. It's a plug and chug thing. So you put the numbers in and then you calculate the minimum resolution based on that. So I'll let you do that at home. Okay. So you can type in those numbers yourself. And then here's another example. That you can put in and work on the depth of focus. Now the question here is what happens when we transition from I line to G line? Does the resolution go up or down? Well, if you remember the spectrum, I line was a smaller wavelength and G line was a bigger wavelength. So if we go from smaller to bigger, our minimum resolution, right, will go up. So we'll be able to resolve. We won't be able to resolve as small things. So you want resolution to be minimized. Okay, unless you're making big stuff. Like if I'm making a MEMS device and the smallest thing I got to print is 1 micron, I'm not going to buy an I-line stepper at $4 million. I'll buy a G-line stepper at $500,000 or a contact printer at $250,000 that's used, right? All right. So what do you think? Based on the discussion, photolithography engineers want to increase the depth of focus or decrease the depth of focus? Yeah, you'd like the depth of focus to be as high as possible because it makes your life easier as an engineer. Okay. Let's see. Gotta move some boxes around here. When going from G to I line, now we're going from the higher wavelength to the lower wavelength, we can make smaller CDs. So CDs, by CDs, I mean critical dimensions, right? So the smaller the CD, the smaller I can print, the smaller the critical dimension. So not everything that you print is critical. There's only certain things that are real critical. In the case of transistors, it would be the gate. The gate size is what determines how big your transistor is, how many transistors you can put per square centimeters, how fast they switch, because if they're smaller, they switch faster. So how many calculations per second can you do, and all of that. Okay, but when we go to smaller CDs, then we lose depth of focus, the ability to focus. So now we've got to have focus control systems on the fly on these machines, and we have to have very flat surfaces, so we might need to polish. Okay. Also, when you make really small things, and you remember, we're doing layers, right? So one layer has to align to the previous layer, right? So if we flip it over, right, they have to be aligned. And the smaller they get, the harder the alignment tolerances are, the finer the alignment tolerances. So if I'm trying to make a line, a conductor, and I've got to line it up with a hole in the insulator so that when I deposit and pattern the conductor, they're lined up, and my conductor's not over here and my hole is here, and then I don't have that connection between the layers, right? The interlayer connections. I'm out of luck, right? So if I make things smaller, I also have to be able to align things better too. Okay, so there's a lot of things that go on with that. All right, since we only have 2 minutes left, next time we'll start with how the process works in photolithography.